Okay. Then the other part we want to look at the amino acid replacement. So this is a continuation of last week's lecture. We talk about the KAKS analysis or DNDS analysis, non-synonymous changes. And we do talk about like the empirical data, like we can observe, we try to observe a lot of protein sequences and look at in the homology sequence what type of changes occur more often than the others. And so this is very similar. But the other, we also can look at the chemical physical property. So the other, this approach was taken in the 70s. Like a Grandson used distance metrics to describe how likely or how similar between two given amino acids. And just to remind you, actually, I put this slide with all the different amino acids here. I think this is also from your textbook, and maybe from the, I think, chapter 1, or they repeat in this chapter, just to show you the chemical structure of the amino acid and the similarity or the grouping of all these amino acids. So in this type, you know, if the chemical physical property are similar, Grandson give a short distance. For example, leucine and isoleucine, the distance is equal to 5. But on the other hand, if the two amino acids are very different in the chemical physical structure and property, then they give a large distance. For example, here is the tryptophan and the cysteine. So in this case, he assigned all the different distance between the amino acids, among amino acid changes. Then they can use this distance to calculate the distance between two protein sequences, and purely based on the chemical and physical property. And based on the Grandson distance, we want to look at what's the correlation between the chemical physical property and the observed frequency in our sequenced sample. So here you can see if the Grandson distance is shorter, we observe the replacement more frequently. We observe this type of mutation more frequently than the others. So that's shown in the first two bars here, right? So the first two bars, the distance, the Grandson distance is at the smaller end, and you occur more frequently compared to all the others. Put another extreme is to the end of this histogram. Towards the end, the Grandson distance is like 186 to 215, and the probability this type of replacement being observed is very, very low. So this is observed. So this histogram represents the observed frequency in each class. So this also shows you one thing I mentioned last week is our empirical data. That's like the frequency of those replacements occur in our natural population is more or less agree with the chemical physical property, and which also makes sense because the protein is made of all these amino acids components. If the property is similar at the same site, it will more likely to still keep the protein structure and also maybe its functional equivalence. So this is to show you the two types of analysis has very high correlation. And this is what we call exchangeability, like how likely from one change to the other. So just this is a slide from your textbook. Just try to let you know how to read it, because here is in the amino acids are in a chain, but the R amino acid occur twice. That's because they occur twice in the codon table. Remember last week when we separate 2,4 degenerate and 4,4 degenerate, there's no 6,4 degenerate. Because when we consider degeneracy, we only consider it within a single box. So here the leucine is 2,4 degenerate site, but immediately in the next section, the leucine is a 4,4 degenerate site. So that's the CHAU-TI table we arranged. So here the leucine has like 2 in parentheses and 4 in parentheses. That means this. And also it's described in the figure legend. And that's the exchange probability, how many mutations and how likely from one amino acid to the other. So there's a different way to look at this.